This is the code snippet. We have a main entry point, and this function will be invoked inside the main by passing in an argument initialized with a value of 2 into this function. And this function is going to take this argument, making a copy of the arguments into K, and then perform some additional assignment, returning 50 at the end. And once the function returns, and then this main exits in the following line. But let's just look at this example closely, see how it is related to call stack. Inside your computer, it keeps track of the stack pointer inside a memory boundary, depending on the OS stack memory, which can go up or down, which depends on your operating system. The important thing to note is that inside your call stack, it is used to store all of the bookkeeping variables, instructions, and execution orders. So you can think of this call stack as the means for operating system to keep track of all of the execution orders in one spot. Let's look at the main function portion of the snippet. In main, both X and Y are initialized on the stack. So remember, your program keeps track of all of the bookkeepings, executions, and orders. Initializing X equals 2, Y equals 1 gets stored in that order on the stack. X equals 2 gets stored at 100, Y equals 1 stored at 99. And now your stack pointer, which is your top, points to 98. That's what happens in the first line. These two happens in the first line of your code. Now let's look at the next one. This one gets tricky. This is passing your argument X into a function, which returns something that gets stored inside this Y. Looking at this, X is passed into a function by value. Why? Well, because we know this function takes an integer K, and this integer K is not a pointer. This integer K is definitely not a reference. Therefore, we're passing X into this function by value. Now, what does that mean? By value means that a copy of the argument is being made inside that function, which allocates a separate space on the stack for K. So there is a copy of X being made by virtue of passing X into that function. And what is X? X is 2. And this 2 is K inside a function that requires an extra storage. So that's 4 bytes, right? Because integer is 4 bytes. That happens at memory address 98. Now that we are 3 activation frames deep into this, and 2 right here, memory address 98. Let's continue on and see what happens inside the function with respect to a call stack in the next slide. Now that we're inside this function, and remember we are at 98. What happens at 97? Let's look at the very first line, integer Y. The declaration of your integer Y sets aside 4 bytes of memory space. So that requires an activation frame, which means your top pointer now is pointing at 97. However, Y initially has an undefined value because you have not assigned any value to it. The value of Y has an undefined, which is a question mark here. However, at line 2, K equals 8. As soon as this happens, your program goes into that call stack. And because K is stored inside this memory 98, its value now is changed to 8. Therefore, we see 8 here. That's what happens at line 2. And the other thing that happens at line 2 is we have Y equals 10. Notice that Y was undefined, but as soon as your line 2 is evaluated completely, Y has a value of 10. Lastly, at line 3, this function returns with a value of 50. Let's look at what happens next in the call stack. The question is, what happens when functions returns? When this function returns, the computer pops the local value Y and K. Why? Well, because this function is now out of stack. Well, because this function is going to be out of scope. Everything you have, including the local variables like K, which is a copy of the original argument, and also Y, which is local to this function, both of these local variables are popped off of the stack. Popping these values off of the stack simply means lowering your stack or top pointer back to what it was, which is line 99. This is where the top pointer goes back to after the function returns, basically back to where we were invoked, the function inside main. And notice that the values of Y and K are still sitting inside of memory address. Your program is not going to clean up the side effect, leaving these values in their original memory space. But the important thing to note is that top is now back at memory address 99 with a value of 50. because we're returning 50. Let's look at what happens next. So far, we've illustrated calling a function once. If you have a lot of function calls, meaning one function calls another, which calls another, with lots of local variables strewn all over the places, you would need a lot of memory, right? Your call stack is going to be used to keep storing these things. Eventually, your call stack may not have enough space to store these instructions. As soon as the function returns, y is going to have a value of 50 because y equals function call x inside that code snippet. Let's go through another example, and this time let's consider, instead of passing arguments into a function by value, let's consider passing the arguments into the function by reference and see how that is going to change our call stack in the next slide. Our function, as illustrated now, takes, instead a integer value, is taking a reference variable. And this reference variable is k. What is a reference? A reference is what we consider as an alias of another variable inside the memory. So remember, we pass x into function, and now that x is being passed in as a reference variable k, which means k is really x. Instead of storing k in activation frame with the memory address 98, we're storing the address of x in that activation frame. So now you can kind of see what is being stored in your call stack, depending on whether that variable is passed by reference, passed by value, or passed by pointer. The difference between passing by reference and passing by pointers is very similar. Namely, you're storing the address of the original object. However, passing by value means that you're making a copy of that original variable inside that activation frame. Now remember, regardless whether you're passing by reference or passing by pointer or passing by value, inside the function, the very first thing the function would do is to make a copy of whatever gets passed in. That reference will be a copy of the original reference. If that object is a pointer, that pointer is made a copy of inside that function. So is the value. Hopefully this illustrates the call stack with respect to passing variables from one function to the other, either by reference or by value. This is a very high-level description of how call stack or a stack frame or activation record works. In reality, call stack contains much more information, including the return address that the call function needs to return to the calling function. So there is this concept of function pointers. It also contains some additional information as we discussed. The beauty of the call stack is that each call function always finds the information it needs to return its caller at the top of the call stack. And if a function makes a call to another function, a stack frame or activation frame for the new function call is simply pushed onto the call stack. Thus, the return address required by the newly called function to return to its caller is now located at the top of the stack. The amount of memory in a computer is finite, right? So only a certain amount of memory can be used to store activation records on the function call stack. If more function calls occurred, then can have their activation record store an error such as Stack Overflow occurs, right? This is the problem sometimes when we write recursive calls, or you have an algorithm that requires the recursive solutions to compute. And as you know, recursive function call is very, very expensive for the reason we just described.